Demonstration problem number 1. If the coefficient of static friction, mu sub s, between a 50-pound crate and the floor is 0.40, what horizontal push must Cuthbert apply so that if he pushes any harder, the crate will just start moving? The givens. The coefficient of static friction, mu sub s, is 0.4. V sub x, the velocity in the x direction, is 0 because the crate is at the threshold of motion. It is not yet moving. The acceleration, a sub x, in the x direction is also 0. This means that all the forces are balanced along the x-axis by Newton's first law. Likewise, v sub y, the velocity along the y-axis, is 0, and the acceleration along the y-axis, a sub y, is also 0. Newton's first law also applies along the y-axis. All the forces are balanced along the y-axis. The weight force, F sub w, is 50 pounds. What is the unknown? We need to know the push so that if he pushes any harder, the crate will just start moving. But what opposes the pushing force? That would be the static friction force. Remember that static friction increases in response to an applied force up to a maximum value determined by a characteristic of the two surfaces in contact, which is the coefficient of static friction. If we don't push at all, there is no static friction. If we push with a small force, the force of static friction will balance that. The forces will be balanced and the crate will not move. If we push harder and harder, static friction will increase up to the maximum value. Since the crate will still be at rest, we will use Newton's first law to solve the problem. What are the equations? We have established that the crate is at rest both along the x-axis and the y-axis. This means that Newton's first law must be applied along both axes. To write Newton's first law, we must first draw a force diagram. We first draw the crate on a horizontal surface. We consider the forces acting on the crate, both along the x-axis and the y-axis. We consider contact forces and field forces. The only field force that we have here is the weight force or the gravitational force applied by the Earth from the center of the Earth. This is not a contact force. It acts downward. That's F sub w, the weight. In response to the weight force, there's a normal force, a vertical force, which balances the weight force. The normal force acts in the upward direction. It's provided by the surface that the crate is sitting on. Then there is the applied force of the push. It is opposed by the static friction force, which increases in response to this applied force. Now that we have our forces on the crate, we then collapse the crate to a particle at its center of gravity. This becomes the origin of our new coordinate system. We then put all the tails of the force vectors at the origin, or at the center of gravity of the crate. So the push acts in the positive x-axis direction. The static friction force, which is a maximum value of static friction because the crate is at the threshold of motion, acts in the negative x-axis direction. It is balanced by the pushing force, since the body is still at rest by Newton's first law. Along the y-axis, we put the tail of the weight force vector at the CG at the origin, and likewise for the normal force. The normal force balances the weight force. The equation. Since velocity is constant along the x and the y axes, write the first law for both. We know that if velocity is constant, then the total force is 0. Since force is a vector, we must write the first law along each axis separately and independently. Therefore, we write F net of x, or the total force along the x-axis, is 0, and F net of y is 0. Now substitute. First symbolically and then numerically. The net force along the x-axis, F net of x. The net force, remember, is two things. By the first law, the net force is 0 for a body at rest. But the net force is also the sum of the forces. That's where the free body diagram comes in. We go to our force diagram and we look at the x-axis and we see that the net force along the x-axis is composed of the push, which is positive, and the frictional force, which is maximum static friction at the threshold of motion, F sub f, which is negative. So we write that the net force is F sub p minus F sub f. But that means that we need another equation. What is F sub f, or maximum static friction? That is coefficient of static friction, mu sub s, times the normal force. For the normal force, we go to the first law along the y-axis. F net of y, once again, is two things. The body is at rest along the y-axis, and so the total force is 0. But the net force is also the sum of the forces. back to the force diagram. In the y direction, you have the weight force, which is down. That's negative F sub W. It's balanced by the normal force provided by the surface that the crate is sitting on. So you have that the net force in the y direction is the normal force minus the weight force, which is 0. But that brings up, what is the weight force? Remember that the weight force is mass times the acceleration of gravity. Since we're dealing with pounds and we're in the British system, the magnitude of the gravitational acceleration, g, or the more formal notation shown here, is 32.2 feet per second per second. So along the x-axis, we have that the pushing force F sub P minus F sub F, the frictional force, is 0. Solving for the pushing force, we have the pushing force in magnitude is F sub F. F sub F, the frictional force, is mu sub S times the normal force. So we make that substitution. The normal force by the first law along the y-axis is equal in magnitude to the weight. So we have that the pushing force is mu sub S times the weight. Now substituting numerically, coefficient of static friction mu sub S is 0.4. We multiply that by the weight force, which was given to be 50 pounds. We get 20 pounds. Pushing force is 20 pounds. If we push any harder than that, then the block will transition from static friction into sliding motion or opposed by kinetic friction.